going to discuss about towards a wavelet-based dynamical adaptive climate model. Over to you, Professor Nicholas.
Thank you very much, Imran, for the introduction, and it's great to be here. I told my daughter I was going to Pakistan to give a talk, and she was surprised that I could go there so quickly. I'm going to be continuing. I'll start again from the beginning for those of you who weren't there last time. And I'm going to be giving an overview of a wavelet-based method for climate modeling. So this is a long program I've been working on for many years, and it illustrates how adaptive wavelet methods can be used for partial differential equation problems. And it's an alternative to adaptive mesh refinement, AMR. So if you're familiar maybe with AMR, which is used a lot in, for example, what would you say, cosmology type calculations, it's an alternative to that. So this is joint work with some collaborators, a couple of collaborators in France, Florian Lemarié, who's in Grenoble, and he has been helping me with the ocean part of the model. Thomas Dubos, who has been at the origin of this, and he's in Paris, and he's helped me with the atmosphere part. So these are the two main components I've developed so far in the Earth system model. And my former PhD student, Matthias Eppner, who did a lot of the development of the shallow water code, so the two-dimensional version of the code. He's now back in Germany working in a private company. So what's the kind of the roadmap here? How do we develop a climate model? And our goal here is to investigate how adaptive wavelet methods can be used in a very realistic problem, and one of the big challenge problems in modern science, which is climate modeling. So we started small, we started slow. We started with the shallow water equations on the plane using a certain special discretization that comes from geophysical fluid dynamics. So shallow water equations, they're two-dimensional equations that model flow in a very shallow layer. So for example, they model surface waves. So you have an equation for velocity components and then layer depth. So that's the base, the simplest model you can have for geophysical flow in the atmosphere of the oceans. And then what we did is we extended this to the sphere. So what changes there? The sphere has a different topology from the plane, and that's a fundamental difference. It's a spherical topology, and there's a basic geometrical fact that you cannot tile a sphere uniformly. In other words, when you discretize the sphere, there's going to be necessarily a certain number of unique points or special points. So you have to deal with that. And also the grid is going to be changing locally. And there's various solutions to this. We use a solution where we start with an icosahedron and you project the edges onto the sphere, and then you subdivide the edges. So unlike on the plane, you'll have 12 special points which have a different valence, a different connection. Okay, so you have triangles, and then you also have hexagons and pentagons. So because you have a local grid that's changing from position to position, that raises a lot of technical issues, and you have to be careful to control the error. Then the next step was to take this two-dimensional model on the sphere and add layers. Okay, so now we have a three-dimensional model in a thin shell. So if you look at the Earth on the left, we know that both the atmosphere and the oceans are very thin compared with the diameter of the Earth. And so we have layers. And why do we have layers? It's because the motions in the atmosphere and oceans at large scales are primarily two-dimensional. Okay, so it makes sense to have layers rather than a three-dimensional grid. We only adapt the grid horizontally, not vertically as well. Although there's a little bit of there's a certain way in which we also adapt vertically. And we then have two different versions, an atmosphere version and an ocean version, but it's built on the same machinery, if you like. What's the difference? The atmosphere is compressible and the ocean is incompressible, and they're both hydrostatic. So the equations are a little bit different and a lot of the physical models are different, but the numerical analysis is the same. So how does wavelet adaptivity work? I'm going to take a simple example, and the simple example is just a step function. Oops, step function here. So I've got a sudden change. It could be like a front, and I'm going to expand the function u of x in a wavelet basis. And so what are the ingredients of the wavelet basis? You've got two families of basis functions. The phi's are what is called the scaling function, and they give you a basis at any given level of resolution. So here we've got 1, 2, 3, 4, 5, 6 different levels of resolution. So we have the coarsest level of resolution. So that's the coarsest grid. And then we've got another of basis functions psi, which are the wavelets. And what the wavelets do is they encode the difference between any two levels of resolution. So what we do is we sum over all positions at a particular scale j, and then we sum over all scales. So in principle, you could go infinite number of scales, and that would be exact. Here we're going to just stop at a certain stage. Here's where the wavelets live. So far, nothing is adaptive. This is just the multi-scale way that wavelets see the function. But this multi-scale way allows us to introduce adaptivity. So what we can do is these coefficients, the expansion coefficients in the wavelet part, tell us about the variation of your function at the position k and the scale j. So if we then only keep those coefficients whose magnitude is greater or equal than epsilon, we would only keep these red points. And so this is a key point of adaptivity, because the only points we need to keep are these red points. We can throw away all these blue points because there is no variation in these smooth parts here. Okay. And mathematically, if you do this, so if you threshold with a threshold epsilon, you have a control on the L infinity error of your approximate solution. So if you just reconstruct with those significant wavelets, the error is order epsilon. If you consider the order of the wavelet, so n, you can think of it like polynomial order. The polynomial order of your wavelet, and the threshold gives you an estimate on how many of these red points there are. So the script n is how many points you need. And the computational complexity is going to be proportional to this script n. And combine these two estimates here. You say for a given error, for a given number of points, script n, this is what the error is. So that's the principle of adaptivity. But so far, we have not solved a partial differential equation. All we've done is kind of image compression. It's saying we can take this picture, this function, and we can represent it with many fewer points in this way. And by changing epsilon, it's just your tolerance. It's how much error you're willing to accept. So what about for a PDE? So generic PDE involving time derivatives and space derivatives is something like this. These are our wavelets. We can do an inverse wavelet transform to get our scaling function coefficient. So that gives our solution at position k and scale j. From this, we can use our favorite, for example, finite difference or finite volume method at each of these scales to get derivatives or differential operators. And all this is in linear complexity in terms of the number of wavelet coefficients we keep. And remember, this n, script n, depends on epsilon. Okay. So now if we go back to our picture here, we have our front. And now imagine that it's in an advection equation. So say it's moving from left to right. Here's our significant wavelet points, which I've now put in blue. We need to take into account that if there's an advection, say it's moving from left to right or from right to left, you need to prepare the neighboring points. Okay, the grid needs to be prepared. And so what we do is we add nearest neighbors at the same scale. So that's prepared for the solution going left or right. Now, if it's a sorry, yep.
So by these identifying these points, you are discussing about with the increase of with the moving of the wave, the distance between these points is increasing.
No, it's all I'm saying is imagine you have an advection equation, okay? And you're solving it with a time stepping method. So you go from one time step to the next. Imagine also that you have a CFL criterion of 1. Okay, so that's a stability criterion. What that means in one time step, your front could move one grid point to the right, or maybe one grid point to the left. But our adaptive grid didn't include these points, so you would have a problem. There's nothing for it to move into. You don't have sufficient resolution. So you prepare those points, you add them into your adaptive grid. Okay. Now the second part, what about these neighbors? So this is at a finer scale. So the scales are factors of 2. And so if you had a nonlinear equation, a quadratic nonlinear equation, so if you multiply 2 sine waves together, for example, like a quadratic nonlinearity, you can make a scale 2 times smaller, okay, or 2 times coarser. That's a basic property of multiplying sines or cosines. And so we do the same thing. You could, so for example, if you have a Burger's equation or an equation where you can steepen, where the gradients increase, in one time step, you could get a scale twice as small. And so we also add these neighbors here, right? And then we're prepared for the gradient increasing. Okay, so now we have all these points. Now we take our time step and we solve it on the red points. And then we do the same filtering again, the same thresholding. So we take away some points and then we take another time step. So this is the basic idea of how you use this wavelet adaptivity to solve a time-dependent PDE. And the key ingredients are the filtering, the adding the adjacent zone, and adding the neighbors at the same scale is good for CFL of 1, kind of advecting back and forth, and adding neighbors at the nearest scale 2 times finer is good for steepening, for making steeper waves. Okay, so how does this work on this sphere? It's the same idea, but a little more complicated because you have this more complicated topology. So the way to make this work, what you need is a coarse grid, which I said is the icosahedron, and a way to refine it. Okay, so here's a sequence of 3 grids on the sphere. And the way it works is, imagine that we have our solution on this fine grid. You have the vertex values, which is like the scaling functions. And then you do a restriction to the coarser grid. And then you try to interpolate the missing values using the data on this grid. And you take the error. And the interpolation errors are the wavelets, the wavelet coefficients. And you just keep doing this, each time restricting, recording the interpolation errors, and that gives you your forward transform. And then the inverse transform, you start with the vertex values, and then you prolong to the finer grid, and you add back in the interpolation errors. Okay, so you can interpolate, but you've got an error and you can add them back in and you keep doing this. So this is the forward transform. This is the inverse transform. The interpolation errors are precisely the wavelet coefficients we talked about earlier. And so the idea is if the wavelet coefficients are small, the interpolation errors are small, and you can leave them out. You say, I'm happy with the error that we get from just interpolation. Okay. And this kind of scheme where you have this hierarchy of grids works for any topology, any complicated geometry. You just need a coarse grid and then a way of producing this hierarchy of finer grids.
Professor Kevlahan,
Yes.
what is the role of the underlying topology here? The method apparently is just a discretization by using some triangulation method, right?
Right. So
yeah, when we are moving, particularly when we are moving from left to right, so what is topologically changing there?
So the topology doesn't change. The topology is always spherical topology, or it's a discrete approximation of the sphere. But where it makes a difference. So if you were on a plane, if you just had a rectangle, you would just have squares, and all the squares are the same. It's homogeneous. Whereas here, if you look carefully, each of these triangles is a little bit different, right? They're all slightly different shapes. And as I said, you have some special points. You have some pentagon points. And so the difference is it's always spherical topology, but you have to, it's kind of a technical challenge, is you have to keep the information about the local geometry. And there's another problem too, is imagine that we kept refining because we want a very fine grid. The geometry of these triangles, there'll be certain triangles that will have very bad shapes. They'll be very acute, very kind of long and thin. And so one thing I'll explain later is you have to kind of fix that up. You have to move the grid around to improve the properties. So the basic idea is the same, but there's technical challenges.
Okay, thank you.
Good. Maybe I'll just skip over this. This is just the kind of the algebra of how you do it on the sphere. Although there's one additional step I would like to say is when I said you go from so this is a restriction steps. Whoops. So you're going from the fine grid. So J+1 is fine, J is coarse. So here's where you calculate your wavelets. So you take the difference of the values on the exact values on the fine grid compared with your interpolated value. So this is the interpolation error. And then your restriction is given here, but we have this extra term. So if we just had this blue term, it would be subsampling. Okay, so if you go from your fine grid to your coarse grid, if you just left out every point, so if you just left out all these red points, you would get this blue. But we do this additional step called lifting, and we add a linear combination of these wavelet coefficients. And what that does is it allows us to conserve certain important properties. And usually the property you especially want to conserve is the mean. Okay, so if you just subsample, you won't conserve the mean. But by doing this lifting step, you can conserve the mean, or you could conserve other things. So what that means is your approximation, each scale should have certain properties. Okay, it should not lose certain properties, and the main property you don't want to lose is the mean. Okay, so this is just an illustration of how this works on the sphere, and these tilde, these S's here, you need to, that really encodes what the wavelet transform is. Okay. So now, if we want to solve geophysical fluid dynamics equations, so equations in the atmosphere, the ocean, we need to use a good discretization. And this is one of the challenges that I found when I started doing this with Manimura. who's now in Delhi, so postdoc with me. We did this in an engineering point of view where we do finite difference method, we controlled the error, but in the ocean and atmosphere, you're always very under-resolved. And so they want you to use what are called mimetic methods, which are methods that conserve certain quantities exactly, discretely. So the key point for Earth system models, atmosphere, ocean, is you want to conserve exactly certain things, such as energy and mass. So mass is very important because you're going to compute for very long times and your simulations are under-resolved. You must exactly conserve mass. It's not enough just to say we conserve mass to accuracy 10⁻⁷ or something. So to do that, you need a certain discretization, for example, called TRISC. And so we just took this from that community, and it's a very nice method because you derive the discretization from discrete Hamiltonians. So in other words, you have a Hamiltonian formulation, you discretize the Hamiltonians, and then the equations of motion come from the discrete Hamiltonians, and that means you build in these conserved quantities. Okay. And here's where another technical problem comes in. And this technical problem comes from the type of discretization we're using. It uses a staggered grid. So staggered grid means that some variables are on some grid points and other variables are on other grid points. And so one of the other technical problems we had to solve here was a wavelet transform on this staggered grid. So the different variables on different grids. So the icosahedron was on the triangles. We saw that earlier. That's the primal grid. But then you have what they call a dual grid. So if you take the midpoints of each edges and you draw lines through those, you get a hexagon. And that's the dual grid. And on the sphere, you have triangles and hexagons, but you have, as I said before, these special points where you get 12 pentagons. So scalars are at the centers of the hexagons, velocities are at these edges, and circulation or vorticity is at these triangle points. So you've got this very careful arrangement of the different variables. Why did they do this? Essentially to conserve mass and to be able to calculate fluxes. So it's a finite volume, finite difference method, and this allows you to calculate fluxes of mass into the hexagons. It allows you to calculate circulation or vorticity around the triangles. And so it's been very carefully designed. But then we have to worry about how do we compute a wavelet transform on this funny grid. Okay. And so, yeah.
Yeah, Professor Nichloas, what
Yes.
do you mean by shallow water?
So shallow water, it's what I said very early on at the beginning. So shallow water means that you imagine you have the ocean and you average in the vertical direction. So you average in the vertical direction. So what you'll get is a two-dimensional equation, but where the variables are the two components of velocity and the height of the water column. So that's a good approximation where you have very long waves and shallow depth. Okay, the waves are long, the wavelength is long compared with the depth of the layer. And so what we're going to do is use this shallow water approach, but then we're going to stack up many layers. So if you had many, many layers of this, and this gives you a three-dimensional equation that that allows you to, in fact, relax the shallow water assumption, because essentially you have lots of these shallow waters.
And regarding to discretization, so you are the main thing is that you identify the points and then taking the convex hull of those points topologically. or geometrical energy?
I don't quite know what you mean by convex hull in this case. They're all on the sphere, right? So all the points
Yeah,
are on
yeah,
the
yeah,
sphere.
yeah.
The black points, these black points are on the sphere, but then it's
Ah, okay.
it's the edges that are important. Okay, the edges are the red edges here; those are the triangles. But then you can have another grid, which is a hexagon grid. Okay, so
Yeah,
if you
yeah,
had
yeah, yeah.
squares, then both grids would be the same topologically. They'd both be squares. But if you have triangles, the other grid is going to be hexagons.
Yeah, okay, okay, okay.
Again, I don't want you to pay attention too much to this, but these are the equations you get. The discretized equations, you get equations for mass, equations for mass-weighted temperature, and then the ocean, this is buoyancy. So this is the thermodynamics, essentially, and then the momentum or velocity equations. And the K is showing you have one of these at each layer, so each vertical layer. So you essentially have these three variables in the simplest version of the problem. Now, in the wavelet approach, you have different scales, so that's very important. So here we have the fine scale. We have the fine scale down here at 1, and we have the coarse scale, and we have an adaptive grid. So imagine that you wanted to calculate gradient of B is Bernoulli. You don't need to worry about it. Divergence of flux, curl of velocity. So you have some differential operators that you need at the coarse scale. There's two paths you could take. You have your fine variables here. You could restrict them and then apply the differential operators, or you could apply the differential operators at the fine scale and then restrict the results to get these here. Now on the grid, at any given point, sometimes you can do this, well, you can always do this, but sometimes you can take this route because you have the fine values, and that should be more precise. And so to make this whole method work and be consistent, you need to take both paths. In other words, you could go this way or this way. And what that does is it puts constraints on the differential operators and the restriction operators. So the key thing to not break conservation of mass or conserving circulation, which is like vorticity, or not to produce artificial vorticity, is you have these commutation relations between restrictions and the differential operators. And so that helps us design our wavelet transform. So in other words, these relations tell us what the restriction operators should be for each of these: restriction of height, restriction of velocity, restriction of Bernoulli, and so on. Okay. So again, this is a little bit technical, but I just wanted to explain that the wavelet transform process is connected here to the grid, but it's also connected to the differential operators that we're solving. Okay, I'll skip over that. Okay, so now I'm going to move on to some examples, and we have to think a little bit about what this really looks like in a realistic application. So what I've shown is here on the sphere, if the sphere were the size of the Earth. So we're really now modeling the Earth. And the J here is the number of refinements of the icosahedron. So each time we subdivide the edge of the icosahedron, J increases by 1. So J equals 0 would be the icosahedron. And here we've subdivided the edge 4 times, 5 times, all the way up to 14 times. So the N is the number of points you get, the number of grid points. And the delta X is the grid size. So the grid size here goes from 480 kilometers to 400 meters. Okay, and I'll show some results where we have a roughly 400 meter resolution on the Earth. So the advantage of this adaptive method is you can get very, very fine resolution, but very, very locally. So I mentioned early on that if you just subdivide the edges and keep doing that, so making smaller and smaller triangles, eventually the triangle geometry becomes very bad. You get very long, thin triangles that have bad numerical properties. But we have to have this hierarchy of subdivisions. The other thing I said is for the wavelet transform to work, all you need is a coarsest level of resolution that you refine. So typically what we would do is we would decide on a coarsest level of resolution, say 5, and we say that's the coarsest grid we need. We're not going to go any coarser than that. And then we're going to optimize it by moving all the points around to make it as uniform as possible. So making all the triangles as close to equilateral as possible. And there's a couple of different algorithms we can use to do that. And then from that coarsest grid, then we just keep refining by edge bisection, and things should be fine. Okay. So we have this hierarchy of grids. We have this optimization of the coarsest grid. And as I said, you can just keep refining. So typically when you're running a simulation, you think, well, what's the coarsest grid I need? And what's the finest grid I need? And you specify those. The actual grid you get at any location is just controlled once again by this error tolerance epsilon, the same error tolerance. So in principle, all you need to do is set this epsilon, the relative error tolerance, and the grid automatically refines and changes in order to achieve that. Now, I'm just going to do this fairly quickly, but I said in the 3-dimensional case, we have these different layers. Okay, so we stack up our shallow water equations in many layers, and there's 2 choices for a coordinate system: Eulerian, where the coordinate system is fixed, and Lagrangian, where it moves with the flow. In other words, the coordinates follow these interfaces between the layers or material surfaces. And so we made the choice of using so-called Lagrangian coordinates. So Lagrangian coordinates are ones that float up and down as the flow changes. So if you have more mass moving in, the coordinates, the interfaces move up. The advantage of that is you have no flux through the interfaces, so it simplifies the equation. Okay. Now, the disadvantage is that because the grids float up and down, they could get very close together, and that could give you very bad properties, and the grid could even collapse. And so we have to do some remapping. In other words, every so often we say, well, our grids have moved too much, and we're going to remap them onto a target grid. Okay. And that can introduce a kind of vertical adaptivity as well. So if we optimize the target grid, we can improve the properties of the vertical grid as well. Okay, so this is the maybe the 3rd ingredient of our method is these floating or Lagrangian vertical grid with the remapping. So that's intrinsic, that's the 3-dimensional part of our method. And I'm just saying here it has to be conservative and there's a certain order. Okay. And then the grid adaptation strategy is essentially what I said before, but you do it in each layer. So in each layer, you apply the adaptation algorithm, and then you just repeat this over all the layers. And the final grid is the union of the adapted grid over all layers. So in other words, it's in columns. Okay, so we have horizontal adaptivity only. And that makes it easy. And it's also very natural for these Earth system models, because things like radiation or clouds or precipitation, they all work on columns. Okay, so you need a data structure that's of columns. So what you end up with is a data structure made up of columns, but where these columns change size locally. Okay. Horizontally adapted grid. So now I'm just going to finish with some examples, and then we'll have some time for questions. So this is going back to the shallow water, so just 2 dimensions. So on the sphere, shallow water equations, and I'm showing the relative vorticity for a turbulence case. So it's an ideal case. It's just turbulence on a rotating sphere. And what it allows us to do is test how well the adaptivity works in a very turbulent case. Because initially people said, well, in turbulence, there are these vortices everywhere, so adaptivity is not going to be very helpful because you always have activity. So here we're going, the coarsest level is 5. So we optimize level 5, and then we went down 1, 2, 3, 4, 5. So 5 factors of 2, that's 32, I guess, 32 times finer grid locally. And so what you can see here is, even though we have vortices everywhere, the finest scales are only required very locally in these filamentary structures. So we nevertheless get a really good advantage from the adaptivity. And there's even some regions here where we only need the very coarse grid. So even in this very kind of homogeneous turbulence case where there is activity, it seems almost everywhere, the adaptivity gives us good results. And now we can use look at a more realistic case. So this is now the 3-dimensional model. Okay, so this is like the atmosphere, and we've got more realistic physics. We have temperature, and we're solving, again, a test case that the people who develop atmosphere models use to evaluate their method. So this is a test case coming from that community. And what I'm sorry, I clicked on my mouse. And what we're showing here is the solution at a certain time of this particular test case, which models, it's a very simple model of atmospheric flow. We've got temperature here, zonal velocity, velocity in this direction, and vorticity, and the adaptive grid. And you can see that in this more realistic case, again, we get an advantage from adaptivity because we only need to put the finest resolution very locally, and we have large regions where we can retain the coarse resolution. And in fact, the adaptive grid looks similar to the vorticity, which is what we would expect. Okay, so these are just pictures to relax, I guess, at the end of the talk. That was the atmosphere model. What do we need to do differently for the ocean model? Well, as I said earlier, one of the main differences for the ocean model is we use incompressible equations, not compressible equations. We use volume penalization for coastline boundary conditions. So as you know, another difference in the ocean is not all of the ocean, not all of the Earth is ocean. There's land masses, that's where we're living. And so you need to have a boundary condition at those places. And if you think about it, in an adaptive method, it's not obvious how you implement those boundary conditions because the coastlines have complicated geometry, and you want to be able to resolve that geometry as you adapt the grid. So we use a special method called penalization, which is where you modify the equation rather than actually explicitly implement the boundary condition. And that's a method that works well with the adaptive method for the equations. I've also, with some colleagues in France, developed a similar penalization for bathymetry. So that's the kind of the topography of the bottom boundary condition in the ocean. And that's for a similar reason. And it actually is a good method even for non-adaptive cases. The final extra detail for ocean modeling is that you have to take into account the fact that you've got very different timescales. You've got the timescale of ocean circulation, like the Gulf Stream, how the flows move around in the ocean, which is quite slow. But then you've got very fast surface waves, like tsunami waves that travel at hundreds of kilometers per hour. You need to separate those two timescales. Otherwise, your code would be far too slow. And so what people use is something called barotropic, which are the fast modes, and baroclinite, which are the slow modes, splitting. So essentially you split your equations into a fast part and a slow part. This means you have to solve an elliptic equation. And so you need a method to do that. And we use the wavelets to do that.
Even for the ocean, the study is for the hydrostatic?
So for the ocean, we use hydrostatic as well. So hydrostatic models are still very common for the ocean. The ocean is incompressible, and we use a hydrostatic approximation. There are some non-hydrostatic models for the ocean. We could extend to that, but I think for the problems we're looking at, hydrostatic is a good enough approximation. And we use a Boussinesq approximation as well. Okay, so another ingredient is, if you like, the physical model. So I haven't talked about this yet, but in Earth system models, you have two basic components, what's called the dynamical core, which is the fluid dynamics and the thermodynamics. And then you've got what they call the physics parts, which are usually separate and model things like cloud formation or rain or radiation. And in the ocean, the physics component is a vertical diffusion model. So you diffuse various quantities vertically in each column, and you use it's a way of modeling turbulence. So TKE means turbulent kinetic energy. So you have a vertical turbulent model in each layer, and that diffuses both buoyancy, so density, and momentum between the layers. And at the top and the bottom, at the top you have a wind stress, and at the bottom you have a bottom friction. So that's an additional component to the model. Okay, so I'll skip over that, and I'll just show you some results. So here, again, you want to solve a certain test case. So what we have here is flow in a channel. So let's just move that away. So it's called upwelling. So essentially, it's like you've got, this is the bathymetry. So this is the ocean bottom. And here are our different layers. And you can see our grid conforms to that channel geometry, and you have a wind blowing over the surface in a way that brings upwelling, it brings water up from the bottom. And this is a very important thing along coastlines. It's how nutrients come up and feed the fish near the surface. And so there's a test case that looks at this. So here is our adapted grid. So I just have a zonal channel. So here is the fluid, and the green is the solid part, so like the continents, and here's the velocity. So not so interesting when you look down here, but we can do a cross section. And so what we're doing is now a cross section, and we've compared with a standard ocean model. So Croco here is a standard ocean model. Here is our wavelet model, but run non-adaptively, and we're showing temperature and the velocity and this is the vertical velocity. So here you can see the upwelling. You get flow going upwards here. And qualitatively, there's some small differences, but considering these are fundamentally completely different models, and also this model is on the sphere, and this is just a regional model on the plane, they're very close. And we can do the same thing. Adaptivity, so we've got two different levels of adaptivity, and so we can get similar results even in the adaptive case. And here's, sorry, I'll go back.
Yeah, why spherical model is good for the ocean? Okay, this is clear for the first picture when you was discussing about the hydrostatic model for the whole Earth. But for the ocean, why this spherical model are better?
So it's not always better. And in fact, Croco, this model here is a regional model. So you just take a small portion of the ocean, and then you have boundary conditions. You have to design boundary conditions. But the wave, if you want to look at global flow, so you want to look at a global circulation model, then it has to be for the sphere. Yeah. Another thing you could do is you could just tell the model you want higher resolution in a local region. So in other words, you wouldn't be determining the fine grid based on the threshold, the error threshold. You would just say, well, in this region, New Pakistan or something, you want a finer grid. And that would give you a kind of a local model. It's what's known as a nested model, where you have fine grid locally. But you're right. And in other examples, if you just want, like in the Red Sea or something, you only want that region, it doesn't really make sense to use a global model.
Yeah, thank you.
But we're always thinking, and I think we're thinking in the context of a climate model where you really need the whole Earth, both for the ocean and the atmosphere.
Yeah.
So this is another example. And again, it's more just a pretty picture, but it's an unstable baroclinic jet. So you start with a jet. Baroclinic means that you have gradients of density horizontally and vertically, and those gradients of density drive a flow. It's unstable, and these baroclinic jets are very important in the ocean. Here we have our grid, our refined grid. Here we have the density perturbation, and here we have the vorticity. So again, it's flow in a channel, so idealized flow, but you can capture this very intricate structure by putting your resolution where you need it. So you're getting a good resolution of these baroclinic jets with these very complicated structures with wavelets. And this is the density perturbations here are you kind of even see this in the ocean in some cases, where you have less, for example, if you have an outflow from a river or between the Mediterranean and the Atlantic Ocean, you have a difference in density, and you get these density-driven flows.
Are there vortices appearing in the ocean model too?
Yes. So this is, if you look closely, you can see vortices here. There's more filamentary structure, but there is another test case I'm working on now for another paper, or it's more, I guess, a fundamental investigation where we look at Western boundary current. So Western boundary current is like the Gulf Stream, and the Gulf Stream, you generate lots of vortices. So yes, indeed, you do get these vortices, and they have very interesting dynamics. They're very important for ocean circulation, and also for things like marine life, because they transport nutrients.
Interesting to know. Thank you.
Okay, so I'm just going to finish now. We've got about 10 minutes left with some open questions. So one question is that I said there's these physics components that do cloud modeling, for example, or radiation. And you might say that these they're called parameterizations. They should know what the scale is. So our method is changing the grid resolution dynamically. So in each location, you can get finer or coarser resolutions. but the physics model, the parameterization, doesn't necessarily know about that. So you might want to change your physics model depending on what the resolution is. And there's been some attempts here, what are called scale-aware parameterizations. And that's because physics is sometimes resolved and sometimes parameterized. How do you define? So maybe the grid refinement criteria should depend on what's happening in the physics, what's happening in the clouds, for example. Maybe there's some mimetic criteria. Mimetic means you want to guarantee that you conserve certain physical quantities. So mass conservation was something like that. Another problem I've been working on with a student, I have a new PhD student, Hamid, working on this, is the problem of data assimilation. So this is not so much an issue for climate, although they do assimilate data, but it's necessary for numerical weather models. So the idea is you have your model and you have satellites and you have ships and you have people in their back garden with a thermometer, and you want to put all that data into your model. And there's the method of data assimilation that says how you incorporate that data into your model in an optimal way. And maybe we can use our adaptive method to do that better, to how we put data into our model. Oops. Okay, and here's the last page, some conclusions. So I showed you in a model that's based on Dynamico. I don't think I explained that. Dynamico is the new French climate model being developed in Paris. So we're using the same discretization, but making a adaptive version of it. We use this Lagrangian vertical coordinate with remapping. We have a multi-scale representation. So that's what the wavelets give you. It gives you this multi-scale view. The dynamic adaptivity, so you adapt the grid at each time step, is controlled by a local estimate of the interpolation error. And this gives you a vertically uniform, horizontally adapted grid. So many columns, your data structure is a set of columns of different sizes. And it's an adaptive overlay on an existing discretization. So in other words, you give me the discretization and I make it adaptive. Okay, it's independent to some extent. I didn't mention this, but of course, to be useful, this must be parallelized. All the big machines are parallel, so we use MPI to make it parallel. We've got dynamic load balancing and a hybrid data structure. Large grid compression achieved at high resolution, so that makes it more efficient. You're using your resources more efficiently. You only put the resolution where you need it. And so we're still working on various things. I didn't even mention the assimilation here. We could try to do more adaptivity on the vertical grid by changing the target grid. I've got a new project with a master student on simple dry physics for planets. So that means take the atmosphere model and use a realistic, include realistic physical effects in addition to just the fluid dynamics, and then maybe some scale-aware subgrid scale parameterizations. So in other words, the physics should change how it works when the resolution changes. So that's all I have to say today, and thank you very much for watching.
Thank you, Professor. Thank you very much for this very elaborative talk. Though I'm a pure mathematician, I'm working in algebra and algebraic geometry. Okay. So, but I try to follow, but you explain it really, really very well. So
thank you very much. Yeah, I know that it was, some parts were quite technical, but at least I tried to give at least a general idea. So if we've got a few minutes for questions, Mohammed, maybe I could.
Okay, Adnan, you can unmute yourself now.
Hi. Hello, doctor. How are you?
Hello. Good.
Okay, fine. So it's not a question, but I just want to know about a little more about the Lagrange vertical coordinate system. I mean,
sure.
Is it updated Lagrangian? I mean, how you model your dynamical theories? static models?
So it's a Lagrangian vertical grid, arbitrary Lagrangian Eulerian.
Okay,
Okay. So it's an ALE type method, and so what that means is that that's a floating coordinate system, but then every so often we do a remapping, conservative remapping onto a specified
every
grid.
step. You mean
not every step? No. So typically
okay.
It would be every 10 to 15 steps.
10 to 15, okay.
So that's what you control in your method. And for now, so if we go back, let's see, whoops. So if you look here, this is an example of in the ocean, the kind of grid we have. This is a hybrid grid. So you can see that it adapts to the bathymetry, but then it gets very flat at the top, very uniform at the top. And so when we take time steps, each of these grid levels is floating, it's changing a little bit. And then every 10 to 15 time steps will remap on in each column back to this grid, back to the original grid.
Yeah, okay. Now the question is because what I feel is the most difficult part is about the degrees of rotational degrees of freedom with ALE. So how far you can tackle those rotational degrees of freedom? I mean, if we have this something rotating inside the domain.
Okay, I don't quite. Let's see. The rotational degrees of freedom. So all the variables are still on these. I
mean, maybe I will put it like that: the mesh tangling. So maybe that is the right way to say this mesh tangling, how to handle the mesh tangling, because that's what I feel quite a difficult part to handle those. I mean, if the mesh is distorted.
Oh, the mesh is distorted. Okay, in this case, you're talking about the vertical mesh being distorted or the horizontal mesh?
Mean, because I was dealing with only the standard ALE approaches. So
okay.
So if I see that if you are able to handle those, I mean,
okay. So the important point is we only have ALE in the vertical grid. So in each column. So each of these, so we don't, because it's only one dimensional, we don't have the problem of mesh distortion in terms of wrapping around or anything.
Fine.
So we're separating, that's a very important point. We only have ALE vertically. Horizontally, it's an Eulerian grid, but an adaptive Eulerian grid. So we don't have those problems that ALE has if you're doing it, say, in a two-dimensional grid.
Okay, so then basically you are taking advantage in and disadvantage out.
Exactly, that's the idea. That's the idea. We're trying to take the best of each.
Okay, fine. But in that case, do you think that it's enough flexible enough to apply for some bioengineering applications? Maybe hemodynamical problems. Maybe.
I think it's specific for this layered geometry. So we have in the ocean and atmosphere, you have these layers.
Okay. Fine.
And so we're separating out the horizontal and the vertical. So it won't apply to cases where you really have homogeneous vertical horizontal. It's really specific for this case where you can have columns and each column is the same vertically. Okay, so our remapping is always one dimensional and that really simplifies things.
Okay, interesting. So your software, this name is Dynamical, right?
So my software is called WaveTrisk. Okay. I should have put that in. Dynamico is a non-adaptive atmosphere model in Paris. And so we're using some of the discretization, but it's called WaveTrisk.
So it means that you already have this validated your own software. Is already validated or?
Yeah, we've written the software. I think you can get it. It's on Zenodo in one of the papers in GMD. Actually, I'm very. It's kind of silly, but I didn't actually. I don't think I gave the name of the code.
I think we have your name, so we'll find it anyway.
Yeah, you can find it from my name. I should have written it. It's a bit silly for me not to have given the name of my own code.
But normally, normally people do other way around. So they every time put their own stuff, and rest is just ignore it.
So here, what I'll do is I'll just do it wave Trisk. So if you Google wave Trisk, if you can see that.
Yeah. Okay. So my question was, it's already in a validated form. So it's already well documented and validated.
Well, I wouldn't say it's well documented. It's documented. So we're still working on it. So I'd say it's an experimental code. So it is available, but it's a work in progress.
Because the problem I was facing after my PhD, it was about this mesh tangling. So then also this, if we have this rotational degrees of freedom, so inside a fluid domain, if I have this some object which is rotating, so then the standard ALE approach, don't work anymore. So then then the idea was to go for the updated Lagrangian some other ways, but I find this quite interesting. Maybe, we instead of vertical, we can also think about in horizontal way. So
yeah, it's true though that for Lagrangian methods horizontally, you do have this mesh tangling. People have tried it. So there's someone called Hilary Weller at Essex in UK who's used these Lagrangian methods. And they also have some sort of remapping, but it is more complicated because you get this grid tangling. It wraps around and so on.
Yeah, and maybe one last question if you have time.
Sure.
I don't know. Okay, how about the time? It's like how long it take to compute some very trivial test case?
It really depends. It depends on the test case. It depends what resolution you have. It depends on the compression. If you look at my papers, I do give the most recent paper. If you go to my website actually it's a couple of years ago now, we'd give some timing comparison with other codes. And basically what you have is a measure for the time per grid element or something like that, and how that scales.
And for the time discretization, so you use the standard, say a Kirk-Nicholson or fractions theta scheme?
We'll use typically a Runge-Kutta scheme, just a third or fourth order Runge-Kutta scheme. And when we do the barotropic mode splitting, then you have a special scheme so you can harmonize those two modes, the fast mode and the slow mode. Okay. Are there any other questions? Sorry.
Yeah, maybe for FEM spaces, you have the linear or even the higher,
we're not using finite elements. But it's a second order method. So it's a finite volume, finite difference method, and it's second order in time and space, or in space.
Okay, great. Thanks a lot. I had a lot of information. So it's
good. Thank you. Good. Well, thanks very much for listening. And I'm glad we could get this talk and make sure it happened.
Yeah. Thank you, Manda sir. Thank you very much for your questions. And are there any other questions from someone? Oh, okay. If this is the case, let us thank Professor Nichloas. Good morning to you.
Good evening to you. It's the evening over there. And I'd like to thank those who came for coming in the evening and letting me not have to get up too early.
Thank you very much. Ultimately, we make it. And I hope we will make it sometime in the usual routine time.
Yes, that would be very nice.
Yeah.
Okay.
Thank you, Professor.
Okay. Thank you so much. Thank you.
Thanks for the invitation. Thanks for letting me come back and start again. And I'm glad everything worked out. Have a good evening.
Thank you.
Bye.